lovely Orgo folks. Today we are going to do counting signals part 2. So let's get right into it. Now I want you guys to be very, very clear when reading the question, because what we just did is a cyclopropane. What we're doing now is a cyclobutane. A lot of times students will memorize either the triangle or the square, and on the exam they won't pay attention to what the question is actually asking, because they're like, oh, Rosemary told me the answer is 4, right? No, wrong. And no, read the question in front of you, right? So cyclobutane works a little bit differently, but don't worry, we're going to do the cis and the trans. First, we're going to do the cis, just because it's on the left, why not? As I drew for the cyclopropanes, I kind of made these in 3D and I color-coded each environment. The two greens may be a little bit different, difficult to tell apart, so I'll go ahead and make it a little darker. Anyhoomst. Cis means that they're on the same side, they're pointing towards the same environment. Trans means that they're pointing opposite. So both methyls, they're going to be the same. You guys should probably know that by now. They're exactly identical, line of symmetry, all that jazz. The hydrogens opposite of the methyls are also going to be equal to one another because they're both attached to a carbon that's attached to the same stuff, and they see hydrogens. So they are identical. Now, the other two carbons is where it gets kind of tricky, because the hydrogens pointing up and the hydrogens pointing down see a completely different environment, because the environment on top of the plane has 2 methyls. The environment below the plane has only hydrogens. So these 2 on the top will be exactly the same, actually, and the 2 on the bottom will be exactly the same, but they're different than one another. This is not true when we look at the trans molecule, because now the environments on top and on the bottom are equal. So the methyl and the hydrogen, the green hydrogen, I'm not even going to explain because it's getting annoying by now. But on these 2 carbons, the hydrogen pointing up here in red is next to a methyl and next to a hydrogen. This purple one now is not the same, because it's next to 2 hydrogens and across from a methyl. If you look down here, though, this hydrogen is next to a methyl and next to a hydrogen. So you get this crisscross. Instead of being across from one another, they crisscross like this. So at the end of the day, you will actually have 1, 2, 3, 4 hydrogen signals for both. So you get the same total number of hydrogen signals, but the arrangement in space is different, and it's important that you guys understand that concept. As I mentioned previously, I left these 2 to do last, but I also decided to include a different way of drawing the important other examples that I did. So these are important that you guys know, the ones I'm running over the laser with. So I drew them in 2 different ways. Whatever helps you see it best. I just hope something helps. I am going to focus on these 2 now, and I will draw them. Actually, I won't. It's fine. Anyways, sorry about that. Brain fart. So we're going to use the same idea that we just used for the cyclopropane and butane examples, but now we have a cyclohexane, which is a lot bigger. The reason I want to do this last is because we have the quadrant that we made, right? And we also have the top versus bottom perspective that we just did. What I mean by the quadrant is we see this line of symmetry here and here. This is important because we know that these 4 areas are the same as one another. They're all exactly equal. But now we know that what's on top of the plane and what's under the plane aren't necessarily different. In the cis example, the top environment and the bottom environment are completely different. So the hydrogens on the bottom, aka dashed, are all going to be the same as one another, all 4 of them, but they are not going to be the same as the ones pointing up. Excuse me, the ones pointing up are all going to be the same as one another, but they are going to be different than the ones pointing down. As well, we can, or I don't know, whatever. Sorry, English is not my first language. This hydrogen on the OH and the hydrogen on the OH, those are going to be completely equal to one another. And this last hydrogen, the one in like the maroon color, those two are equivalent. So we can say that we have 1, 2, 3, 4 hydrogen signals. And when they are trans, we actually have the same environment up top and on the bottom. So we will see that crisscross again. Okay, so OH up, these 2 up hydrogens, or wedged, are going to be the same, and they're going to be the same as the ones pointing down on the other side. The green ones pointing down here are going to be the same ones as the green pointing up here. I suggest draw this out, draw it in 3D, play around with it so you're able to see what I'm talking about. The answer again will be 4 hydrogen signals, but I want you to be able to see why and how they're arranged in space. We're going to go through now and do carbon signals, and we're going to start here and work backwards. So this carbon and this carbon, they're highlighted in red, and they are exactly the same. And then we also have this, and this, all 4 of which are going to be exactly the same. So we have 2 carbon signals. Believe it or not, we actually have the same answer here, because even though things are arranged differently in space, the carbons will be exactly identical. So this is your answer. As promised, here are all the other examples, and let us go through it. Again, symmetry down the middle. Same idea as the hydrogens, but slightly less complicated. So those 2 carbons are the same. These 2 are the same. These 2 are the same, and now we don't have to worry about diastereotopic or anything, because the carbon can't be diastereotopic. And then we also have this yellow one. So all together, we have 1, 2, 3, 4 carbon signals. Next one over, and yes, I am going to zoom out and show you all the answers at the end. These 2 purple are exactly the same. This one is all by itself. This blue one is also by itself. And then we have 1, 2 yellow ones. These 2 red ones are equal, and this blue one at the bottom is all by itself. So all together we have 1, 2, 3, 4, 5, 6 carbon signals. We already did this one, but I highlighted it for you anyway. And I'll just write down 2. Next up, we have the same idea going on where we have this line of symmetry right here. So these 2 methyls are the same. These 2 carbons will be the same. I'm not sure why I skipped highlighting it, but it's fine. And then these 2 reds will also all be equal. Or these 4 reds, I should say, will all be equal. So altogether, we have 3 carbon signals. Now, going down, we get more and more colorful as we go down. Here, we have the 2 methyls are equal. 2 of these carbons are equal, the orange ones. This red one is all by, or this pink one is all by itself. These 2 red ones are equal, and this blue one is all by itself. So, if we count 1, 2, 3, 4, 5. Next up, we have our line of symmetry down the middle again. we will have a total of 4 carbon signals. Here we have our 1, 2, 3 unique carbons. Alrighty, folks. This is where it gets a little bit weird and people kind of get confused because of the whole like space issue, right? This is different than the hydrogens, and I'll make it super different and color that differently. Because even though the hydrogens can point all these weird different directions and have crazy things going on, the carbon is just a carbon. So it's going to be on the same plane. So these two are equal, these two are equal, and this one is by itself, just hanging out. So we have a total of 3 carbon signals. The exact same thing is true here, because even though the orientation of some things in space changed, that carbon itself did not. So we have 3 carbon signals in both. Same idea over here for the cyclobutanes. We are going to have 1, 2, 3 carbon signals for each.